All righty. Good morning, everyone. Today we're going to do two things. We're going to go over the test. The grades have been posted, and I made a lot of comments on the sides. I didn't make any comments on the paper, so you can see all the stuff directly in the comments section on the side. If you have questions as we go, that's fine. Although maybe you should keep track of the questions. I'm going to go fairly quickly just so we can get through it. And if you have questions on grading, just email me if you thought I missed something or you want me to take another look. I'm fine with that. So here we go. So test one, solutions. Okay, so number one said we have this function and it's on the interval from 0 to 1. So we have a parabola that starts up here at 3 and at 1. One kind of looks roughly, God, that's terrible. Looks like that. So you're talking about the area under that. So yeah, that's an easy one to do, but we wanted to see if you can do the Riemann process. So this is where you chop up 0 to 1 into n pieces, and the individual width of each one is 1 over n. And so if you do the areas of all of these things, the first one would be, it's always like this. It's the width, and then it's the function value at the first point. We're using the right endpoint, so it would be one copy of 1 over n. That's the first area. The second area also has a 1 over n, and the third one has a 1 over n, the fourth one has 1 over n. So I'm just going to do this one little shortcut of factoring out the width. So the width is common to all of them, so you can distribute it back out. The next one is 3 minus 2, then 2 copies of 1 over n. So you could write that as 2 over n. And that's squared. And then you'll have 2 times 3 copies of n squared. All the way across until you get to 3 minus 2 n copies of n squared. So if you got that, that was a pretty good chunk of it. And that's exactly what we've been doing over and over and over in these problems is just start. And in this case, it's a lot easier because it's just 0 to 1. Anyway, 1 over n, we've got, all these 3's, 3, 3, 3, 3, 3, 3, 3, 3, and we have n terms, so we have n copies of 3. There. The next one, all of these things in here have 2's. So if we wanted to regroup, and I could probably do 2 steps here once, but I'm just going to do it like this. This is 1 over n squared. This is 2 squared over n squared. The next one is 3 squared over n squared, all the way across to n squared over n squared. So factor out the 2's, minus 2's, and we get to that. So we'll have 1 over n. This will be 3n minus, and I probably could have done it in 2 steps, but you notice that now I've got an n squared in the denominator for each one. So I could factor out that denominator, or 1 over n squared. And I'm left with 1 plus 2 squared plus 3 squared all the way across n squared. And then that's the formula that I need to use. So if I do that, I get 1 over n, 3n, 2 over n squared, and then the formula for that, you just look it up in the book, n times n plus 1 times 2n plus 1 over 6. And that's the general formula for n. So if I knew n, I could plug it in. I wanted to end up taking a limit of this, so I think I'm going to have to clean it up a little bit. So let's see what we can do here. One of these n's will cancel. The 2 and the 6 will cancel to leave a 3. That's all I want to do in that step. So I still have 1 over n, still have 3n, and then I'll have minus, and in this fraction, I've got n plus 1 and 2n plus 1 on the top, and on the bottom I've got 3n. Like that. So now I could distribute this 1 over n, and I get 3, and I multiply those together, 3n and over n, minus, and then I've got n plus 1, 2n plus 1, and 3n squared. If I distribute that n over here as well. So you get down to this, and, well, a couple ways to do it. One is just take this and plug in bigger and bigger and bigger and bigger and bigger numbers. The other is to multiply this top out as n 2n squared plus 3n plus 1, and then divide each term by 3n. And if you do that, 2n squared over 3n squared is 2/3. 3n over 3n squared is 1 over n. 1 over 3n squared. And now if you take the limit as n goes to infinity, these last two terms will drop out because you're dividing by larger and larger and larger and larger numbers. So those will end up going to 0. So all that's left is 3 minus 2/3, which is 7/3. Which of course you could have gotten by just doing the integral from 0 to 1, but the point was for you to interpret all this. So if you got sort of anything that looked like this, that was a big chunk of it, and the rest was just trying to follow it through, and I gave most of the credit for just setting it up. If you didn't set it off, then you just like say, I'm going to pick n to be 4 and work it out. You're like, that's not what we're aiming for. So I gave you some, but this is it. So got to do at least one of those, maybe revisit it on final. Likely to be revisited on the final. There's that. 2, again, I'm going through this fast, but we want this integral, which, good luck. I don't think you're going to be able to do that antiderivative. I don't know what it is. I don't know how to do that, if it's even possible. So we want to use the trapezoid and Simpson's rule to approximate it. And whenever you approximate, don't round. If you round and round and round and round, then your answer is going to be gibberish. So just leave it as much as you can and then let your calculator round it at the end. So we need n equals 4. So at least this is nice that we chop it up into 4 pieces, 0 to 1, 1 to 2, 2 to 3. So I am at least going to need to calculate this function at all of those points. And again, don't round yet. So I'm going to stick in 0, 1, 2, 3, and 4. So when I do, I'll get the natural log of 1, the natural log of 2. Now, you got to remember, I got to square and add it. So this is the natural log of 5, natural log of 10, and natural log of 17. So it's just plugging in 0 through 4 into the function, and it squares it, adds 1, and then puts it in the natural log. And really, that I have this, you can see that each of these widths here is 1. So that's 1, that's 1, that's 1, that's 1. So that's the delta x in the formula. And so for the trapezoid, you'll get, and again, you probably want to use, we'll just use equals, but it's going to be an approximation. So we'll have delta x, which is 1 over 2. Delta x over 2 is part of the formula. And then here, I've got 1 copy of the first height. Then I've got 2 copies of the next one, 2 copies of the next one, 2 copies of the next one, natural log 10, and then 1 copy of the last one. So 1, 2, 5, 10, 17, all in that below. And for Simpson's, which right, I know this is parts A and B, but this says take delta x and divide it by 3. So that would be 1 over 3. And it looks exactly the same, except 2 of the 2's turn into 4s. So it's natural log of 1 plus 4 ln2 plus 2 ln5 plus 4 ln10 plus ln17. And those are the, sort of like the exact trapezoid and Simpson's rule. If you then put it in your calculator, but only at the end, you got a decent approximation, it would be like 6.0218 and 6.0116. If you chopped it off and just said they're both 6, then we weren't really subtle enough. You didn't say how many decimal places, but chopping it off too soon is missing the point. Anyway, there's that. 2 and then 3. 3 was just draw the picture and do the area. And part A was absolute value, which looks like that, like absolute value. You wanted to do the integral from -3 to 8. So -3 to 8. So that, which, you know, integral of absolute value, who knows? You're going to have to break it up anyway. But in this case, you just take, this is badly scaled, but you just take those two areas. And it's a triangle, so it's 1/2 base times height. They're both above the axis, so it's 1/2 base times height for the left one, and then 1/2 base times height for the right one. And they're like, you know, halves of squares, basically. And so this would be 9 halves, and this would be 32. So you get 32 plus 9 halves, which you could write as a certain number of halves, or you could write it as 36.5. Either of those is fine. They're all equal. B, the integral from -100 to 200 of 100 minus 5x. So I know those numbers are big, but it really is just draw the picture. I'm giving myself more room there. Let's see, at -100, definitely not scale here. Plug in -100 and I'll get 600. If I plug in 200, maybe about here.
Sorry, but back from 3A, you said for criticism it's just two triangles.
Yeah.
I thought I just drew two triangles exactly. I'm just a little confused. That's all. Because it just looks like I draw just two triangles.
I did draw. So the absolute value curve looks like this.
Mm-hmm.
I go from -3 to 8. I sketch everything underneath, so I get this triangle here is 3 by 3, and I get this triangle here, which is 8 by 8, and then just do the two areas and add them up.
Yeah, I do the exact same thing.
Okay.
Right.
If I took out points, just I'll look again. Just send me a note to remind me.
Okay.
Now, the only thing you have to be careful about this is when you drew it, it doesn't go through the origin. So if you were to put in x equals 0, it actually crosses at 100. So this thing comes down, and it crosses at 20. So that was sort of the main catch to be careful on. So again, this is two triangles, but you have to figure out that this is 600 high and 120 wide, or width or base and height. Here, this is 180, and this is 900, but this will be negative area, and that'll be positive area. So you take the positive area, which is 1/2, 120 times 600, and you subtract off the negative area, which is 1/2, 180 times 900. And if you work that out, it's minus 45,000. So top area minus bottom, so that's the signed area. It's the answer for the definite interval. C was a little bit of the tricky one here, but if you plot it from 0 to 4, so at 0, you'll get 6, and it's a circle, like a quarter of a circle. You want the whole area underneath, but the top half is a quarter circle, and the bottom is a rectangle. And the rectangle is 4 by 2, and the quarter circle has a radius of 4. So, you know, the rectangle answer is just 2 times 4, so that's 8. And the circle is 1/4 of pi times the radius squared, and the radius is 4. So that's 16 over 4, so that's 4 pi, like that. So geometry. You tried any integration, I did dock you because it just said draw it. Don't use any fancy tools, just use geometry. And then the last one 4. The velocity of an object is 2t minus 8 all squared. And you're talking about basically on interval from 0 to 6. And part A says, what is the minimum of that guy? Well, you have to plot it, look at it, with this parabola type shape. And you can also see that it's a square, so this thing can never be negative, but it could be 0. And so the lowest that you get is 0, and B will be 0 at time 4. So 4 is the answer for part A. Part B, displacement is by definition the integral from 0 to 6. It's just the integral. And so you have to work that out. And yeah, if you knew how to do substitution, which you do, I suppose. If you didn't, then really you can just multiply this out as 4t squared minus 32t plus 64. And then you integrate that to get 4/3 t cubed minus 16t squared plus 64t. Plug in 6 and 0 and subtract, and you should get 96. And I don't know what units that is. If it was feet per second up above, it would be feet. If it's miles per hour, that would be miles. Whatever the units are for distance. C, average velocity is a formula in the book, and that is the integral from 0 to 6 of your function. But then you divide by the width of it, so from 0 to 6. And so basically it's just part B divided by, you don't have to redo it because you already know the answer to the integral. And you divide by 6, and you get 16 feet per second, miles per hour, whatever that is. And then the question is, when do you actually hit that? Do you ever actually hit that average velocity? And you have to at some point. You can't like go less than 16 and greater than 16, but not hit 16 ever. So we can just take our velocity and set it equal to 16 and be real careful, because this will occur when t is 2 or when t is 6. And a lot of people got both, but some people went, okay, that has to be 4, so t has to be 6. But also it can be -4 because you square it and you get that. Anyway, that's test 1. Grades are in there. And you know, it's 14% of your grade right now. Some of you did very well. I think the average is around 80 for the test. If you didn't, you know, if you struggled on this one, there's still a lot to go, but and you can, you know, on the final, show that you did it. I'm not going to curve anything at this point because, again, the average is like 80. But if you have concerns, you know, but maybe haven't been putting in the work or haven't been turning in homework or haven't been getting things checked, all those things you can try and correct. So, again, if you have questions on any of that stuff, just send me a note and I'll look again since I have the test. All right, so we did that. So let's see, where are we? So 6.1, we did that. That was the use substitution methods. 6.2 was the integration by parts formula, and that is, one of those two is due today. I think I don't have the thing in front of me, so look at the schedule on that. And so we're just really working through how do you find these antiderivatives if they're complicated. So if they're easy, you can just do them. If they're in the table, you can do them. If not, you're going to have to do these simplification tools, either use substitution or integration by parts, or maybe combined or multiple integration by parts, or any of these sorts of things. And we also saw this little shortcut here, E8, of how you choose U. So we can go through that in a little bit. We're going to just talk for a little bit about 6.3, do some examples, and then have, I think, plenty of time to do homework. So 6.3 is very specific. It's like of a certain kind, and this is like trig identities to death here. So these are trigonometric integrals. They have very specific types. In fact, we're going to look at 3 three specific types, or three classes of types, and how do you handle each one. So type 1 here will look like things that have sines and cosines multiplied together, but there's going to be a power on each one. So you want to put like a symbol to say that we're going to change the power and redo the integral and try another set of powers. So the book puts like an M here and an N here. So M and N are going to be these like positive whole numbers. We'll adjust those and we'll do the integral and we'll adjust them again, and we might need a slightly different formula depending on what those M and N are. And it'll depend on whether M and N are odd or even, basically. Question? So that's one type of integral that we're going to do. We're going to change these numbers, and you'll have different methods to handle them depending on what these values are. The second class, which are very similar, is where you take things that look like this. The sign of a number times x, and also times the sign of another number times x. So sine of ax times sine of bx. We'll change these numbers and try and figure out how to do this. And I said there's a class of these things. You could have sine and sine, or you could have sine ax and cosine bx, or you could have cosine cosine. So they're all kind of the same. You have very similar methods, but you just change it from sine and cosine. And A and B are just numbers. And we'll put in different numbers, and based on the numbers, you'll get different solutions. And then the last one, which looks much uglier here, it's like part 1, except instead of sine and cosine, we're going to use tangent and secant because they go together. And people love these. So tangent raised to a power and secant raised to a power. And again, in all of these, M and N are positive whole numbers. And A and B are just real numbers. It could be anything you want. And there's lots of symbols. So far we have no numbers and all of this stuff. So we're just going to do a ton of examples of different kinds and see what happens. So I don't know if that looks scary or not, but let's just try and put some numbers in and see what happens. Okay, so for example, the integral of sine squared. Okay, I can't remember if we did this one yet or not, but we can't just do like sine cubed over 3. We can't just add the power up and come back down, because if we then verified it with the derivative, we would end up getting a chain rule, and it certainly would not be this. So the answer is this is not sine cubed over 3. You just can't do that. So sort of technique number 1, maybe I don't know if you want to think of it like trick number 1, is that the sine squared is equal to 1 minus the cosine of 2t, or 2x in this case, over 2. So this is like a double angle identity. If you like trig and you like identities, this is your day. If you don't, hang in there, I guess. It's a double angle. Why did I write trig there? I can't talk and write at the same time sometimes. Double angle identity. You got the double of the angle right there. So if I just replace sine squared with this thing on the right, I've got 1. It's the same thing as 1 minus the cosine of 2x over 2. And I don't know if that looks any easier to you or not, but it is. Because we can do this. This is a multiple of a half, so I can multiply on the outside by this half. And then I just repeat the inside, 1 minus cosine 3. And now, the first one is easy. It's just, I'm integrating 1. So that one, when I integrate that, it's just x. The second one, it's a little bit trickier, but not too bad. This 2x seems to throw it off, but there's a very little baby u substitution in here to get that the answer is the integral of cosine 2x is like sine of 2x, except I have to divide by 2 to balance out the 2 when I do the chain rule to get back to where I started from. So, boom, there's the answer to this problem. So you could write it like that, or I guess, I think in the table it might write it as distribute this half back through. So it's 1/2 x, or x over 2, and then the half and the half for the sine recombine to give sine of 2x over 4. And let's see if I can pull that up quickly. You know, click on it like this. Nope. And the book, and it's at the very end. Yeah. How many windows flying around here? Okay. So if I go to the very end of the book, page 330. Nope, not page 330. I don't know why it's in that. The pen is annoying. Okay, here we go. So back it up just a little bit. Too much. Okay, it is, where is it? Almost done. There you go, right there. So formula 21 in the book is exactly what we got over here. And so you can see that that's how you derive that one. So it's a double angle identity, and then you integrate that up. So that's the example if you just have sine squared. But remember I said we want sines and cosines in there. So another example is I can do sine squared times cosine.
And that will only occur if n is even. If
Well,
n or for n, like, sorry.
Yeah, we'll come back to what is the trick for doing this, and I'll tell you what that is in a second. And we'll come back to it. So here we've got sine squared and we've got cosine, and if you want, you can write this as like cosine to the 1. And so in this case, well, you could write this just simply as u equals sine, and then du will be the derivative of u, cosine, dx. So again, we're just doing a u substitution, so this part right here to get this is du. And what's the first part? Well, the first part we do the substitution is sine goes in here, and that 2 means to square it. So we get u squared du. So if we have something like this, we do a substitution. And now we can integrate this out. 1/3 u cubed, and then replace. We get 1/3, put the u back in, which is sine cubed. And then we can put our plus c. So if it looks like even, and what's the power really of cosine here? There isn't one, so you can think of this as like to the 0 power. You raise that to the 0, you get 1. So it's like an even power for sine and an even power for cosine. And that's when you're going to use these double angle identities. If they're both even, you're going to need to use these. If one is even and the other is odd, you'll be able to do some sort of substitution. You might have to do one little trick in advance, but you'll be able to do a substitution of some kind. And so let me show you that example. So this is even, odd, like that. So let's see. This one looks kind of ugly, but we'll do it anyway. So sine to the 5th.
So it was just, I'm sorry, so the answer was just sine cubed over 3?
That was the final answer, yep.
Okay,
One
clear.
okay. Yeah. And you can verify that, and you should be verifying it. If you don't, well, it might be harder to understand what's going on, but you know, take the derivative of this, the 3 comes down, it becomes a 2, And then we have to multiply by the derivative of the inside, which is sine. It's the derivative of sine, which is cosine. So you'll get sine squared and you'll get cosine. Okay.
I'm sorry if I'm just asking things again. It's just my computer freezes up sometimes. Just want to clarify. That's all.
Nope. Cool. I'm happy with that. All right. So now this one, we've got odd and we've got even here. So this is kind of a new one. And this is where we need to use one more identity well, let's see. The sine squared of x. Let's see. The one identity you definitely should know from trig is sine squared plus cosine squared equals 1. So sine squared plus cosine squared is 1, which means that if I want sine squared, it's 1 minus cosine squared. So you can put the cosine squared here, you can bring it over and get sine squared plus cosine squared is 1, or sine squared equals 1 minus cosine squared. So if you substitute that in, well, what does sine to the fifth mean? It means sine, 1 sine squared, another sine squared, all multiplied together. So we have 5 of them, and then cosine to the fourth. And well, it's like, it looks even worse. But if we substitute in here and here, then we'll get this. We get sine, and we'll get sine squared, so that's 1 minus cosine squared. That's that one. And then we'll get another 1 minus cosine squared, because I've got 2 of them, so that'll be squared. And then the cosine to the fourth, I'm going to leave it like that. Now, why did I do that? Well, it turns out now I can use a U substitution. I've got cosine and sine, so I know this is either going to be cosine or sine. And the complicated part is the cosine part. And the not complicated part, hopefully, will be the sine. In this case, it's negative. So everything's going to have to be sort of deal with that negative there. But let's see how we can put all this stuff in. We've got cosine squared and cosine to the fourth. Well, those I can plug in u. So that'll be 1 minus u squared. And then cosine to the fourth will be u to the fourth. And I don't know how you guys are doing this, but if you look at this sine and this dx together, I can put them together, and that will be right there. So sine of x dx is negative du. And then I just substitute that in for both terms together. If you don't like that, you could just solve directly for dx, which is 1 over negative sine x du. And then you can see when you plug it in, the signs will cancel. So you plug that in, you'll have sine on the top, sine on the bottom. Either way, you get negative du. Negative multiples can be put wherever we want. It's sort of nice to put it on the outside when we get down to that point. So all this stuff is gone, except now we get down to this. Which isn't, I don't know if that looks easier or not. It's like all these powers and stuff, but it is a lot easier than having all of this trig stuff in there. So let me just finish this one up, and we'll take a quick break and come back and look at the other ones. But really, at this point, all you got to, it's annoying that you got to multiply it out. It's not really any good sneaky tricks at this point. So we got to multiply all this stuff out. So square it, and then distribute the 4 on it. So if we multiply just this part out, it would be 1. We would have 2 copies of u squared, and then we would have u to the 4th. So that's just foiling or distributing this square out. So the first one squared, twice the cross middle term, and then the last one squared. Now I still have to distribute the u to the 4th on all of those, but that will be u to the 4th, and then distribute it here. Distributed here will be u to the 6th. Distributed here, it'll be u to the 8th. So it's really just taking this inside term and algebraing it, multiplying out, distributing, and then we get du. Now all of those individual terms are not super difficult. U to the 4th will be 1/5 u to the 5th. U to the 6th term, that'll be u to the 7th. I divide by 7, but I already have a 2 there, so 2/7. And then the last one is u to the 9th over 9. And then I replace. U is cosine. So wherever I have u, I'm going to replace that u with cosine. So I will have negative 1/5 cosine to the 5th. The negative 2/7 becomes positive 2/7 cosine to the 7th. And then the negative distributes out, so it'll be negative cosine to the 9th over 9. It's just to be consistent with these are not short. I don't know if you sort of figured that out at this point. But they'll either use this identity or they'll use that double angle identity depending on which one is odd and which one is even. If they're both even, you have to use the double angle. If one is odd and the other is even, you use this identity. If it's reversed, where the sine is has the 4 and the cosine has the 5, then you just reverse this, and instead of doing sine squared equals 1 minus cosine, you would do the reverse. Cosine squared equals 1 minus sine, and then you substitute that in. And then you get u equals sine instead of u equals cosine. So kind of a lot. There's a lot of trig stuff going on in there. It does take a lot of algebra, making sure not to screw up all these powers. But anyway, that's the first class there. So I think that's probably a good place to take a quick 5-minute break, or we'll come back at 10:30 and then handle the other 2 cases and then see if you have questions on them. So see you at 10:30.